In section 18, we're going to be looking at a new type of function called the exponential function. And definition 18.1 is going to give us that definition. It says that the exponential function with base b is defined for all real numbers x by equation of the form, and then it gives us an equation. Now, it says here that it's defined for all real numbers x. That right there is implying that the domain could be all real numbers. That's the largest possible domain that we are allowed to have for this, all real numbers. You could use less than that, but we are permitted to have that as our domain if we want. And then the equation has to be of the form f of x equals b raised to the x. Remember, b here is said to be the base of the exponential function. So one of the key features of this type of function compared to other types of functions is the location of the variable. The variable is located in the exponent, hence why we call this an exponential function. Exponents are not new. We've seen exponents in a variety of ways already, but we've never seen a variable located in the exponent. Now, there are some other stipulations on this. Your base value has to be greater than 0, and it also is not allowed to be 1. When we say that it has to be greater than 0, that means that it has to be positive, and obviously if it's not 1, then it's not 1. So example 18.1 is going to give us a chance to see how we can use this definition to identify when an equation could be used to represent an exponential function. So let's see. Part A, f of x equals 3 raised to the x. So certainly we have the variable in the exponent, and then our base is going to be 3. 3 would be positive, and it's also not 1. So I'm going to say yes, this does qualify as being a exponential equation. Part B, f of x is equal to x raised to the third. Now you might first look at this and say, oh yeah, it's not something that we've seen before. It's got to be exponential because there's an exponent. Keep in mind what has to be in the exponent. In the exponent, you're supposed to have a variable that is a constant. It's just 3. Your variable is down here on your base. So for it to be an exponential function, you need the base to be constant, and you need the exponent to be the variable. So this is actually an example of a polynomial. This is the kind of structure that we have for polynomials, where the variable is the base and the constant is the exponent. So this does not get to qualify as being exponential. Part C, this one does get to qualify as being exponential. The base is positive and it's not 1. And I know that we have x minus 1 here in the exponent, but as long as we have some kind of variable up there in the exponent, we're going to allow this to be qualified as a exponential function. We'll talk in the upcoming parts of this section about transformations, and this is an example of something that has a transformation, but it's still considered exponential. Part D, we have g of x is equal to 1/2 raised to the x plus 2. This also is going to be perfectly fine. This is exponential. We have the variable located in the exponent, and the base, 1/2 is positive, and the value is not 1. So we're good to go there. On part E, 1 raised to the x. That's the one thing we don't want. We definitely don't want the base to be 1, so this does not qualify as being an exponential function. Part F, we have g of x is equal to -2 raised to the x plus 1. So we definitely have a problem here with this being a negative base. And we're told that in the definition, all of the bases have to be greater than 0. That doesn't work for us, so this is also not going to be exponential. Part G, we have f of x equals 0.32 raised to the x. I don't see any problems with this. 0.32 is positive, and it's not 1. And then finally, part H. Now this one's interesting because it does have a variable for the exponent, but it also has a variable for the base. So this is kind of a combination between a polynomial and an exponential function, and it is beyond the scope of what we're going to study in here, and it does not qualify as being exponential. So we're going to say no to that. Now this is how we can use definition 18.1 to determine whether or not a function is exponential, based on the equation. But the exponential functions can also be further classified based off of what type of behavior we see with them graphically. Let me go to the next slide, and I want to talk about definition 18.2. It says, let f of x equal b to the x be the equation of an exponential function. That's directly coming from definition 18.1. If the base value is larger than 1, then that means that your function is called an exponential growth function. And we'll see graphical examples of all of these things so we can actually see and make the connection with the base value and it being growth, and that'll be coming up soon. Statement number 2, if your base is less than 1, then that means that your function is going to be called an exponential decay function. So every function that is exponential can have this classification done. So example 18.2 wants us to do just that. Classify each equation in example 18.1 that is exponential as either growth or decay. Let's go back to the other slide and let's look at part A. We said that f of x equals 3 to the x was exponential, and that base value is greater than 1. So our base here is greater than 1, so therefore this qualifies as being exponential growth. The next example that we said was exponential was part C, and in this case we also have a base value that is greater than 1. This is going to be exponential growth as well. Part D, however, we have a base that is 1/2, and that base is less than 1. That means that we're going to have exponential decay. And on the bottom row, the only function that was exponential was part G. F of x is 0.32 raised to the x. So our base here is 0.32, and that is less than 1. So this is going to be another example of exponential decay.